All right, good morning, everybody. Let's get started. The last lecture in this course on vector calculus. So today, I should say actually, before I start the lecture, Carrie, who is the supremo of all matters undergraduate, has asked all lecturers to stress to the students to please fill in the feedback forms for the lecturers and the courses. Think of it as a gift to the next generation of students if you help to improve the lectures by giving some feedback. Okay, so today we're going to talk about Stokes' theorem. So Stokes' theorem is named after the mathematician George Stokes. Unlike, as I was saying yesterday, unlike the divergence theorem, which is named after the vector operator, this one is actually named after a person, and it's a little bit ironic because historical investigations have shown that Stokes, the reason that Stokes is associated with this theorem is because Lord Kelvin discovered it and wrote it to him in a letter, and then Stokes later on published it, and it now bears his name. So it should really be, for a while it was called the Kelvin-Stokes theorem, but now it's just known as Stokes' theorem. Stokes' theorem relates the surface integral of the curl of some vector field f. So this is a surface integral, this is the curl of a vector field f. Because the curl of a vector field is itself a vector, this is a vector surface integral. It relates that to the closed loop which marks the boundary of that surface and the line integral of that same vector field around that boundary. So this is the vector surface integral of the curl equals the line integral of the boundary. So this only works for open surfaces. I'll illustrate in a moment exactly what this means, but yesterday when we were talking about the divergence theorem only works for closed surfaces. The Stokes' theorem only works for open surfaces. So let me give you an example of what I mean here. If I have some surface which looks like that, which has some boundary like that, then the line integral round here is your term on the right-hand side. So this loop here is the C. So this here is C. And all of this, that is the surface S. Okay? So that's what we mean when we're talking geometrically, when we're trying to visualize what Stokes' theorem means. It tells me that the vector surface integral of the curl of the vector field that this shape is embedded in, the vector surface integral over the whole surface, is equal to the line integral of that vector field around its boundary. So that's, hopefully, it says the same thing. Yes, it does. And something we'll come back to in about half an hour is the fact that Stokes' theorem only works for what is known as simply connected spaces. So just as with the divergence theorem, it looked at face value like fields which fell off as 1 over r squared, like the electric and gravitational fields. It looked like they broke the divergence theorem. You'll recall that we had this pathological example of a field which we came across a couple of lectures ago, which we'll realise, or maybe you've already realised, looks like it breaks Stokes' theorem, and the reason it doesn't actually turns out to be very similar to the reason that we can get out of the contradiction with the divergence theorem. And that comes down to the fact that for most vector fields, in fact, that you come across, they're not describing simply connected spaces, but I'll come back to that. Okay, so let's do a quick derivation of Stokes' theorem. And what we're actually doing here is we're more or less doing a derivation of the curl. So you'll recall when I did the lecture on the curl, I kind of skipped the derivation of it. What we're going to do now is we're going to do the derivation of one of the three components of the curl. And we're going to see how that leads us to understand Stokes' theorem. So I think Stokes' theorem is a little bit less intuitive than divergence theorem. So again, recall from yesterday, I think the divergence theorem, where the sum of all the sources and sinks within a volume should equate through the flux crossing the boundary, that's kind of intuitive. I think Stokes' theorem is a little bit less intuitive. Okay, so I'm going to take the derivation of the curl of one component of the curl. So again, cast your memory back to last week. The curl is just a measure of the microscopic rotation of your vector field around some point. And so each of the three components of the curl tells you about the rotation of the vector field in the plane perpendicular to that component. So what we're going to look at here is we're going to look at the derivation of the curl in the case of a badly drawn square in the x and y plane. So this would be the k component of the curl, right? So the k component of the curl measures the rotation of the field in the x and y plane. And the definition of the curl, I'll keep over this side, the definition of the curl, much as we had the definition of the divergence being the surface integral of the vector field in the limit that you shrank your volume to an infinitesimally small volume, the definition of the curl is that the curl in some direction of some unit vector n is the limit as an area goes to 0 of 1 over that area times the line integral of the boundary around that area. So that should make sense because, again, as I say, the curl pointing in that direction, if that was the z direction, the curl is the rotation in the xy plane. So you want the limit of the rotation of your vector field in the xy plane in the limit that you shrink down to infinitesimally small. And that rotation is given by a line integral in a loop. Okay, so this is the definition of each of the three components of the curl. So now let's have a look at the example of one particular component, the k component, and we'll consider the simple example of a square in the xy plane. And we'll say that the square is centered at x and y, and we'll say that the lengths of these sides are, this is delta x, and this is delta y, so therefore the area of this little square is delta x, delta y. And you'll see this is going to have some very clear similarities to how we did the derivation for the divergence. So this square is embedded in some vector field, and this vector field has components which operate in the x and y directions. So I'll call those fx and fy. Okay, so those are the components of the vector field which would be operating in the I and j directions. And I will label these sides as 1, 2, 3, 4, and we will sum up the line integral around that square. So if I first look at the line integral on side 1, what I see is that the line integral on side 1 is going to be the fy component of the vector field as it operates at a position x plus delta x over 2y, and it's going to operate over the length of that side, so delta y. So what we're doing here is we're making the assumption that we can treat the whole of the operation of the vector field on that line integral to be happening at here, the midpoint of each of these lines. Just as when we were doing the derivation of the divergence, we assumed that we could have our surface integrals just operating at the midpoint of our surfaces. And of course, in the limit that our sizes and lengths become infinitesimally small, that is correct. Okay. So that's the line integral along line 1. And then for line 3, it's going to be minus Fy, x operating at x minus delta x over 2y times delta y. So if I then sum up 1 and 3, I get Fy as it operates at x plus delta x over 2y minus Fy as it operates at x minus delta x over 2y. And all of this is multiplied by delta y. So that's my line integral summing up sides 1 and 3 of this square here. Now, if I multiply the top and bottom by delta x again, you'll see this is very similar to the tricks that we played when we were deriving the divergence. I put a delta x there, I put a delta x there. In the limit that delta x approaches 0, this becomes dfy by dx, and this term here, dx dy, is just dA. Oh, sorry, it's just A. It's just the area of the square. And if I similarly add up 2 and 4, then I find that that's minus dfx by dy, also multiplied by the area A. So then the total line integral in the xy plane around this loop, that is the k component of the curl, is given by delta fy by dx minus delta dfy by dx minus dfx by dy, all times by the area. And we can see that our definition of the curl is the line integral divided by the area, so we end up with our component of the curl. So that's the k component of the curl, and of course in the full 3D derivation of the curl, you do the same thing for 2 other planes which are perpendicular, and you get your full expression for the curl. Okay. So why is it that with the curl, so the expressions we have derived then are for an infinitesimal surface, why is it that for the curl we can consider only the outer boundary that describes the perimeter of the shape, regardless of the shape of the boundary? So this is the reason. If I imagine now that I have some larger square which I break up into 4 of these infinitesimally smaller squares, again you can see this is very, very similar to the explanation we have of why the divergence theorem only works on the surface. You can see that if I have some surface which I've broken up into 4 small squares, the boundaries of 2 adjacent squares will have line integrals which are operating in opposite directions. So the line integral around here will exactly cancel the line integral around here, and this will cancel with this, this will cancel with this, this will cancel with this, and the only thing that is left is the line integral around the boundary. So imagine I have some boundary like this, and I break it up into small pieces. And then imagine that I've done this in the limit where each of these squares has become infinitesimally small. For this particular square here, my line integral is like this, but for the adjacent square here, my line integral is like this. So these two cancel each other out. And the same thing happens for every square except for those which are on the boundary. So only these squares here, only these regions here, these little areas, only those count to the net surface integral of the curl. And again, you can see then in the limit where these little areas become infinitesimally small, all that you're left with is the line integral around the boundary. Everything else inside the shape cancels. Okay. Okay. So the two-dimensional form of Stokes' law is often referred to as Green's theorem. So Green's theorem says that the line integral around the C, the boundary of some open surface, then is the surface integral of dfy by dx minus dfx by dy dA, and this dA would typically be dx dy if we're evaluating in the xy plane. And this is the expression we have just derived. So this is essentially Stokes' law in two dimensions, and this is the k component of the curl, and it's the expression which we just derived. But Green's theorem is often expressed in the following form. Consider the line integral L dx plus m dy around some shape. So what this is saying then is that this is the component of the vector field, or the component of the field which operates in the x direction, and this is the component which operates in the y direction. So we may identify L as being fx, and we may identify m as being fy. So therefore, making these identifications and by equivalence with the above expression, then we get that this line integral is equal to dm dx minus dl dy by dA, where dA is normally dx dy. Okay, so let's very quickly do an example then. So here's an example. Use Green's theorem to evaluate y cubed dx minus x cubed dy, where C is a circle of radius 2 with positive orientation centered on the origin. So I have a circle of radius 2. Positive orientation is in this sense, and I'll show you why. I'll show you a way that you can remember this in a moment. And this is radius 2. So the expression is saying, give us the integral of this around this loop. So we're identifying this component here as fx, or equivalently as L in the normal expression of Green's theorem, and this then we're identifying as fy, which equals m in the common formulation of Green's theorem. So we want to work out what is d of fx by dy. So that's going to be 3y squared, and d of fy by dx is going to be 3x squared. And we're going to convert these to plane polar coordinates because we're doing a surface integral of a circle, so of course the obvious thing to do is to put this into plane polar coordinates. so I'm going to switch this to plane polar coordinates. So plane r squared equals x squared plus y squared. So we can see that dfy by dx is 3x squared minus dfx by dy is giving me then, so I have 3x squared minus 3y squared. I have a feeling I'm missing a minus. Then we'll see a missing minus. Thank you. Right, so that then in plane polar coordinates is minus 3r squared. So our integral then is going to be theta goes between 0 and 2 pi, r goes between 0 and 1 of minus 3r squared. Now I've taken an expression which was in x and y coordinates and I've changed it to plane polar coordinates, so I have to put in another r, which is the Jacobian, and then I integrate this with respect to dr and d theta. And the theta term, as ever, just turns out to be a 2 pi in front, and then this term turns out to be minus between 0 and 2, r to the 4 is 16, 4, 12, minus 24 pi. So that's how you use Green's theorem, which is the two-dimensional version of Stokes' theorem, to evaluate a line integral by evaluating the surface integral of one component of the curl. So one of the very nice things about Stokes' theorem, and this is similar to the example we looked at when we were looking at vector areas. One nice thing about Stokes' theorem is that it works for any capping surface in 3D space. So I'll sketch on the board badly in a moment what I mean exactly by this, but if this is your boundary here, then the surface which extends from it can be any surface in 3D space. So this is my boundary where I do my line integral. This is the surface over which I'm doing my surface integrals of the curl. These are little loops with arrows on, they're not cues. The direction of circulation is important, right? So the normal expectation is that when people talk about positive or default orientation, it's such that if you're walking around your boundary, you keep your capping surface on your left-hand side. So if you imagine this as a physical hill, you'd be walking around like this, you'd be keeping it on your left-hand side. That's the normal orientation. But the great thing about this then is that, so I have this boundary here, around which I walk. This is the relatively straightforward shape I have here, and I know that the surface integral of the curl on this shape is equal to the line integral around here. But if I perfectly reproduce that shape here, and then just as you've seen me do before, I draw some random shape here, it's the same, okay? And again, it should be obvious that it's the same. The surface integral of the curl must be the same because the line integral around that boundary is the same. So if shapes share a boundary, then because of Stokes' theorem, the surface integrals must be the curls, regardless of the shape of the capping surface. Okay, so let's do an example with Stokes' theorem then. So use Stokes' theorem to evaluate a line integral f dot dr, where f equals z squared I plus y squared j plus x k, and C is a triangle with vertices 1, 0, 0, 0, 1, 0, and 0, 0, 1. With counterclockwise rotation. So this triangle is sketched there. We've come across this triangle before, earlier in the course, and again, the obvious simple tip is that if you're not sure, if you're not sure exactly what the shape is, just draw the points of these vertices. You can tell it's a plane, connect the points, and you'll get the triangle. So, what we're going to need to do then, we're going to want to do the surface integral of the curl. So we're doing a vector surface integral. So we're going to want to work out what is the equation for this surface, and we've got to work out what is the gradient of that in order, the gradient of that surface in order to give us a normal to the surface. Okay? So this surface is described by x plus y plus z equals 1. That is the surface which describes this triangle within the limits x, y, and z all both between 0 and 1. Because we're using Stokes' theorem, we're going to be doing the surface integral of the curl. So we want to know what is the curl of this vector field. So the curl of F is going to be the determinant of the matrix I, J, K, d by dx, d by dy, d by dz of, what are my components? Z squared, y squared, and x. So for my I component then, so the curl equals my I component has, oh, that's nothing, so there's no I component, minus my J component, which has a 1 minus 2z, and then my K component, which has nothing again. So the curl of this vector field is 2z minus 1j. And the way we're going to do this then is we're going to do the dot product of the normal to this surface with the curl, and we're going to project it down onto the xy plane in the way that I think you've probably done many times by now on your problem sheets also. So how do we find out the normal to the surface? So we say that we have a surface which is described by x plus y plus z minus 1 equals 0. I'm just putting the minus 1 in there for bookkeeping's sake. Okay, obviously, when I work out the gradient of this scalar field, the minus 1 doesn't make any difference. So I get the gradient of my scalar field then equals I plus j plus k. Now that you know because of the method that we're about to use, that the normalization of this normal will cancel out with the projection term, but in case you want to bookkeep that as well, then you can immediately see that the normalization of this normal is square root of 3. And if you look at this shape, it makes sense intuitively. So this shape is this triangle facing outwards, going to positive x, y, and z. It makes sense that the normal coming out of this surface should have equal components of x and y and z. Okay, so it makes intuitive sense that the normal to this surface should be something with equal components I and j. The reason that it's useful to bookkeep the normalization is, of course, I could multiply this by any scalar and it would still be a normal. Okay? But then you could potentially run into an error because you would be using normal whose normalization didn't cancel with the projection term. Okay. So I think I have everything I need now to rearrange my expression so that I can evaluate it. So what I have is I have, oops. So I want to evaluate this. This is the surface of the triangle. is the unit normal times by the area. This is the vector area, so it's the unit normal times by the scalar area. And we then recast this as a projection down onto the xy plane. So we now do our 2D integral over some area on the xy plane. Z minus 1j, dotted with our normal, which is our gradient of f. The normalization of that exactly cancels out with our projection term. So you'll recall our projection term, which we did a few weeks ago now, would have been 1 plus the derivative of f with respect to I with respect to x squared plus the derivative of f with respect to y squared, which again turns out to be square root of 3. So there's a projection term in here. And that cancels out exactly with that. And then this dA here will end up being dy. And our region on the xy plane, our D region on the xy plane, will then be x goes between 0 and 1, and y goes between 1 minus x and 0. So the dot product of our curl with our gradient then is just going to be 2z minus 1. So it only has a non-zero dot product with the j term, so it's 2z minus 1. And we want this in terms of x and y. So we know our original expression was x plus y plus z equals 1. So z equals 1 minus x minus y. Therefore, 2z minus 1 equals 2 times 1 minus x minus y. Minus 1 equals 1 minus 2x minus 2y. So, finally then, we end up with our integral between x, 0 and 1, y equals 0 and 1 minus x of 1 minus 2x minus 2y integrated with respect to y and x. There's about 2 lines of algebra, and you end up with an answer of minus 1/6. So those are amongst the trickiest genre of integrals that you have to do. But again, it's all very straightforward. I think really the trick in doing these things through successfully is just bookkeeping, making sure that you're doing every step properly. The maths is at every stage very straightforward. Okay, so I've said that Stokes' theorem only works for simply connected surfaces. What is a simply connected surface? A simply connected surface is best thought of and remembered in the following way. So you consider your surface, and if you want to work out whether or not it's a simply connected surface, and you draw a loop of any size on your surface, and then you see whether or not you could shrink your loop to an infinitesimally small length without it ever leaving the surface. Okay? So a sphere is a nice example of a two-dimensional simply connected surface. We can draw the largest possible loop around the surface, which would be a perimeter like this, and we shrink it, and we shrink it, and we shrink it till it becomes infinitesimally small, and it can shrink all the way whilst remaining on that surface. However, a torus is not a simply connected surface. So here's a bad illustration of a torus. I could draw a loop around the torus like this, and I could not shrink that loop to infinitesimally small without leaving the surface. It would have to cross the boundary of the torus. Equally, I could have a loop around my torus like this, and I could not shrink it beyond the point at which it matched in length the inner radius of the torus. To shrink it further, it would have to leave the surface. So a torus is not a simply connected space, but something like a sphere or a plane is. Okay. So some of you will remember this pathological vector field, which appeared to have, well in fact does have, zero curl, but a large-scale circulation. And now you know Stokes' theorem, you'll realise that that doesn't appear to make sense, because you could have this vector field where you would definitely have a positive line integral if you did a line integral around a loop, and yet the surface integral of the curl within that region would be zero, because for that particular field, the curl everywhere was zero. And it was this vector field. So, this is the famously nasty vector field for Stokes' law. So, minus yi plus xj. So again, if I have a y term in front of the I component and an x term in front of the j component, and if one of them has the other sign to the other one, I have a rotating vector field. The normalization of this would be x squared plus y squared to the half, so that would give you a unit vector at every distance, but if I have this vector field divided by an extra component of square root of x squared plus y squared, then it falls off with distance. So, if I was to sketch that vector field, I would see clearly it has large-scale circulation. This colourful circle here is meant to illustrate a microscopically small ball in that flow. So if I put that ball down in that flow and watched it, this is what I see. I would see that it would move around in that flow, but, as I mentioned previously when I was talking about curl a couple of lectures ago, I would not see that ball rotating. Okay? The microscopic rotation, the curl, is zero, but there is a large-scale rotation. So, it seems like this breaks Stokes' law. The discussion of 2 minutes ago about simply connected surfaces is obviously going to be our way out, but this way out has a lot of similarities with the way out which we found for the divergence law in the electric field. So, you may recall from a long time ago the following. X, y, some angle theta, some point here. And if I'm in plane polar coordinates, then I actually have a unit vector which is in the direction of increasing theta. And that unit vector we worked out about a month ago is minus I sine theta plus j cos theta. And if I then look at the expressions for sine theta and cos theta in terms of the x and y plane here, then I see that my unit vector here is minus I, sine theta is opposite over hypotenuse, so that's y over x squared plus y squared to the half, and that's plus jx over x squared plus y squared to the half. So my unit vector in my direction of increasing theta is minus I y plus jx over x squared plus y squared to the half. Therefore, our nasty pathological field here, minus yi plus xj over x squared plus y squared, is simply described by the unit vector in the increasing theta direction divided by another component, another unit of its length. So then if I consider my vector field here, so I have this vector field which we know is rotating but is falling off, and I consider a loop. I do a circular loop in this vector field, and this loop has a radius of big R, say, let's work out what is the line integral around this loop. So the line integral around this loop, you're going to immediately see, has no dependence whatsoever on the size of the loop. It's just going to be theta goes between 0 and 2 pi. My vector field is theta hat over r. I add in an r, which is the Jacobian, and I integrate with respect to d theta, and this then is 2 pi. So the line integral around the circular loop in this vector field is 2 pi, completely independent of the radius at which you do that loop. So recalling our discussion yesterday about the use of the Dirac delta to get us out of a similar problem with the divergence, what we say is that for this particular vector field, the curl is 2 pi delta 2r, where this is the 2D Dirac delta. And that then allows us to get out of the problem with Stokes' law and this field. And what is the reason that we cannot use Stokes' law for this field? And the reason, again, is essentially the same as it was for the divergence, which is that this vector field, like nearly all the vector fields, in fact, you come across, at least for the first few years, this vector field is not defined at the origin. What does that mean in terms of the discussion we've just been having? This means that we have our spherical space in which we have our vector field, or in this case our two-dimensional representation of it, but there is a hole, a vastly exaggerated hole has been cut out at the origin where that vector field doesn't work, and therefore this vector field is not operating in a simply connected space. So that's the get-out clause for this particular vector field. It's not as general that you get vector fields like this which appear to break Stokes' law as it is that you get vector fields that fall off as 1 over r squared, which appear to break the divergence theorem. But nevertheless, this is such an interesting case that you'll probably see this again as you go through the rest of your physics degree. All right, so in the final 5 minutes then of the course, I just want to talk about the second order terms associated with our 3 new vector operators. That is combinations of div, grad, and curl. So first off, you cannot have a vector. You cannot have an operator which requires a vector field operating on a scalar field, and you cannot have an operator which requires a scalar field operating on a vector field. Okay. So this means that you cannot have the grad of some scalar field, because grad has to operate on a scalar field, but the grad in here has already generated for you a vector field. So this cannot exist. Similarly, this cannot exist, okay, because curl generates a vector field. So grad and curl generate vector fields, so you can't have the grad of those. So these expressions simply don't exist. Curl and div require vector fields, but div gives you a scalar field, so these expressions also cannot exist. So there is no sense in which these equate to anything. They don't equate to zero. They simply are nonsensical and they don't exist at all. There are two expressions which are always zero. And they are the curl of the gradient, that is always zero, and the divergence of the curl is always zero. So conservative fields have zero curl, so that's the reason why the curl of grad is zero, and we demonstrated that the divergence of the curl was zero, I think, 2 lectures back, possibly. Right, there are a few combinations which do exist and which are non-zero. The most important of these is the Laplacian, which we came across briefly a few lectures back. So the divergence of the gradient of some scalar potential, div grad u, is del squared of that scalar field, and is the second derivative of that field with respect to x, plus the second derivative of that field with respect to y, plus the second derivative of that field with respect to z. And that's the scalar Laplacian of that field. There is also a vector Laplacian, which is essentially the same thing, but it's some black holes. It's given by this expression here. It's essentially the equivalent expression that retains for you a vector field. There is this expression. These things are all written down in the notes in case you were rushing to try and write that down. There is grad of div of some vector field. So grad of div of some vector field is given by this expression here. It does sometimes come up, but really rarely. You might probably get away with never encountering this ever again. It's so rarely encountered that it actually has no special name, apart from being called grad div. And that's the expression for it. Don't bother writing it down. This one you will come across, I think, occasionally. The curl of curl is given by the gradient of the divergence of the vector field minus the Laplacian of that vector field. So this one, I think you will have a few derivations and expansions which you do in the second year where you will use this expression. Again, it's all written down, and I think that's almost it. So here we are. In summary, there are only two products of div, grad, and curl which actually mean anything. The most important one you will definitely come across is the Laplacian, which has both scalar and vector forms, and you may, if you're unlucky, come across grad div. Okay, that's the end of the course. So this is, just a reminder then, this was the syllabus of this bit of CP4. Double integrals, yeah. Dealing with an Cartesian, plane polar, and other coordinate systems, yeah. Jacobians, line surface and volume integrals, evaluation by change of variables, yes. Integrals, variables, yes. And that's the syllabus not involved as it existed until a year and a half ago. And then, of course, there is a little extra bit about understanding what probability density functions and cumulative distribution functions are. And that's the end of the course. Thank you for coming along for 12 lectures. Cheers.